From scanning a barcode at the store to streaming this very explainer, lasers are pretty much the invisible backbone of our modern world. But what's really wild is that the biggest revolution in laser tech didn't come from making them bigger or more powerful. It came from shrinking a key part down to the size of just a few dozen atoms.
Okay, so what you're looking at here is something called a photonic integrated circuit. This is the kind of gear that powers the entire global internet, shuffling just incredible amounts of data through fiber optic cables. And right at the heart of all that speed is a tiny, powerful light source, the semiconductor laser. And to really get our heads around the engine of our connected age, we need to understand the quantum leap that made it all possible.
So before we can get to the quantum magic, we first have to pop the hood on a classic, conventional semiconductor laser. This is our baseline, the technology that was about to be completely turned on its head.
The standard workhorse for a long time was called a double heterostructure, or DH laser. Now, the most important part of that name is the active region. You can think of this as the laser's engine room. It's that one special slice of material where electricity gets converted into a powerful focused beam of light.
Now, in a conventional DH laser, that active region is about 1,000 angstroms thick. And that's a unit of measurement that's, it's just mind-bogglingly small. 1 inch has over 250 million of them. But in the world of physics, this scale creates what's called a bulk environment. It basically behaves like a normal slab of material, where electrons can just move around freely inside. All right, this is where the revolution happens. We're about to shrink that active region so dramatically that the normal rules of physics kind of start to break down, and the strange, powerful rules of quantum mechanics totally take over. So what does happen if we take that 1,000 angstrom thick engine room and we shrink it by a factor of 10, down to just 100 angstroms, a layer so incredibly thin it's barely a few dozen atoms across? Everything changes. The physics completely shifts. In that bulk material, the available energy states for an electron are continuous. Think of it like a smooth ramp. An electron can have pretty much any energy it wants within a certain range. But when you get to that ultra-thin layer, quantum mechanics just kicks in. The electrons are so squeezed, so confined, that they can only occupy specific, discrete energy levels, like steps on a staircase. They can be on step 1 or step 2, but absolutely nowhere in between. And this ultra-thin active region is what we call a quantum well. It's a well because the electrons are literally trapped inside it. And it's quantum because their behavior is now totally governed by that staircase of energy levels. And let me tell you, this isn't just some small tweak. It fundamentally rewires the entire laser. So you might be asking, why go to all this trouble? What does trapping electrons on a quantum staircase actually do for us? Well, it turns out it gives the laser a set of incredible new superpowers. By forcing electrons into these specific energy states, we get 3 huge benefits. First, the lasers need way less electrical current to turn on and start doing their thing. Second, they become much, much more stable and resistant to changes in temperature. And third, and this one is an absolute game changer, we get the ability to precisely engineer the exact color or wavelength of the light they produce. And we can actually measure that incredible temperature stability. Physicists use this value called T0, where a higher number means a more stable laser. A standard laser, it might have a T0 around 140 Kelvin. But a quantum well laser, its stability just skyrockets to over 400. That massive leap means its performance stays locked in even when it gets hot, which is absolutely critical for real-world devices. But honestly, the most powerful advantage might just be tunability. Just like this quote says, the wavelength is no longer some fixed property of the material. Instead, it becomes a design choice. We can literally build a laser to produce the exact color of light we need for a specific job. And get this, just by shrinking the quantum well from 100 angstroms down to only 80, we can shift the laser's wavelength from 1.55 microns to 1.46 microns. This ability to create dozens of slightly different colors of light is the key to something called wavelength division multiplexing. That's the magic that lets a single fiber optic cable carry millions of phone calls and video streams all at the same time. Okay, so we've got this incredible new principle. But how do we turn a single, ridiculously thin quantum well into a powerful, high-performance laser that we can actually use? Well, the answer is pretty simple. We stack them. And this leads us to the multiple quantum well, or MQW, structure. The whole idea is to take everything that's great about a single quantum well and just multiply it, creating one bigger, more powerful active region by layering several of them together.
The physics here is just so clever. We stack the quantum wells, but we separate them with these little barrier layers. Now, these barriers are just wide enough to keep the electrons in each well isolated, which preserves that crucial staircase effect. The light wave, though, is much wider. It just ignores the individual wells and sees the entire stack as one big unified engine. This design gives us the best of both worlds, all that quantum efficiency, but with a seriously high power output.
So, where is all of this miniaturization heading? Well, the ultimate goal is to put millions, literally millions, of these nanolasers onto a single computer chip. Instead of using tiny wires to send data between the cores in a processor, we could use beams of light. This is the future of intra-chip optical interconnects, a future where the principles of the quantum well could redefine the very speed of computation itself.